Here we have an example of a Bernoulli differential equation. So we have ty prime minus the quantity 1 plus t times y is equal to ty square. Now, first thing to notice is that this differential equation is not in the standard Bernoulli equation form. But we can easily convert that into a standard Bernoulli differential equation form by dividing throughout by t. So if you divide the whole equation by t, you have y prime minus 1 plus t divided by t times y equals y squared. And this is now the standard form. So we can make our substitution. V equals y raised to 1 minus, notice the value of n in this case is 2, so 1 minus 2. And so we have V equals y raised to the power of negative 1. And then the next step is to differentiate. So V prime is negative 1, y raised to negative 2, y prime. And now if we solve for y prime, we have y prime equals negative y square v prime, which we can easily get by dividing both the sides by negative y raised to negative 2. And now let's copy down the equation that we wrote down in the standard form. So we have y prime minus 1 plus t over t times y is equal to y squared. And now we will substitute negative y square v prime for y prime, and therefore we have negative y square v prime minus 1 plus t over t times y is equal to y squared. The next step is to get rid of the coefficient negative y square on v prime. So let's multiply the entire equation with negative y raised to negative 2. And the resulting equation is v prime plus 1 plus t divided by t, y raised to the power of negative 1, and that is equal to negative 1. And one final substitution that remains is y raised to negative 1. Well, that is our change of variable, v. And therefore, we get v prime plus 1 plus t over t times v is equal to negative 1, and this is the first order linear differential equation, which I have abbreviated as FOLDE. Also notice that this differential equation is not separable, so we will have to solve this using the method of integrating factor. So for the integrating factor, we must integrate the coefficient function on the term v. So let us first start by integrating this coefficient function. So the integral of 1 plus t divided by t with respect to t can be simplified as the integral of 1 divided by t plus 1 dt. And now we can integrate both of these, 1 over t and 1, individually and then add them up together. So the integral of 1 over t is the natural log of t, and that of 1 with respect to t is simply at. At this point, we will avoid adding the arbitrary constant c. And so therefore, the integrating factor denoted by the Greek letter mu is e raised to natural log of t plus t, which can be simplified to t times e raised to t, using the properties of natural log and exponential functions. So therefore, we will multiply the integrating factor to the first order linear differential equation we found after the change of variables. So therefore, we will have t times e raised to t multiplied to the left hand side, which is v prime plus 1 plus t over t times v, and that must equal negative 1 times the integrating factor, which is t times e raised to the power of t. The whole point of multiplying the integrating factor is that the left-hand side of the differential equation, the one with the derivative, collapses down into a product rule. It collapses down into the derivative of the product, v in this case, which is the dependent variable, times the integrating factor, which we found to be t times e to the power of t. And the right-hand side simplifies to negative t e to the t. So, the function that is being differentiated on the left, v times t times e to the t, has to be the integral or the antiderivative of the right-hand side function. And so therefore, we can reach the conclusion that t times e to the t times v must be the integral of negative t e to the t dt. Now, this integral on the right-hand side may be evaluated using integration by parts. So if you use integration by parts, you end up getting t times e to the t times v is equal to negative t e to the t plus e to the t plus some arbitrary constant c. And at this point, we have almost solved the differential equation. So let's isolate v. So we need to divide the entire equation by t times e raised to t. Upon division, we get v equals negative 1 plus 1 over t plus c over t e raised to t. Let me rewrite that function one more time. So the solution we got to the new equation after the change of variables was v equals negative 1 plus 1 over t plus c over t e raised to t. Remember, when we started the differential equation, we started with the dependent variable y. V is a change of variable that we brought into the picture because we wanted to make the given differential equation linear so we could solve it. So although this is the solution to the modified differential equation, it is not the solution to the original differential equation, which is what we seek. And so at this point, we simply bring back our change of variables. So our change of variables was y raised to negative 1 equals v. And so now we can simply replace the v with y raised to negative 1. And that is equal to negative 1 plus 1 over t plus c over t e to the t. And if we raise both the sides to the power of -1, we can have an explicit solution. And so therefore, the explicit solution is y equals -1 plus 1 over t plus c over t e to the t, the entire quantity raised to the power of -1. And we may leave our solution there. Notice that we are not given an initial condition, so this is the general solution of the given Bernoulli differential equation.